Yes, we were doing numericals and let's continue with these questions. Next one. The stopping potential for photoelectrons ejected from a surface by 375 nanometer photons. 375 nanometer photons is 1.87 moles. Calculate the stopping potential for 600 nanometer photons. Now here, two different light sources we can say of different wavelengths we are using. In the first case 375 nanometer wavelength and in the second case 600 nanometer wavelength. So two different lights we are using now. So for in the first case, when the wavelength is 375 nanometers, the stopping potential is found to be 1.87 volts. Then we have to find for the 600 nanometer photons what would be the stopping potential. As we know, the stopping potential will increase with the frequency of light. If the frequency increases, the stopping potential also increases, because as frequency increases, the kinetic energy of the electron will also increase, the maximum kinetic energy will also increase, and when maximum kinetic energy increases, the stopping potential required to stop the electrons will also increase. So since instead of frequency we have wavelength here, so we will see what happens to the stopping potential when wavelength is changed to 600 nanometers. So let's write the equation first. So h nu is 5 plus Ke max. Now instead of this Ke max, I'll directly write EV naught from now onwards, because we are familiar with this now, since we are supposed to find the stopping potential. So h nu plus EV naught. Now for the first case, even I can write it as C by lambda, because lambda it is given in terms of wavelength, not frequency. Now in the first case, two cases are there. We'll solve by case 1 and case 2. First case, lambda is 375 and CH we know, V naught is also given. What we don't know is phi. So what we can do is, take the first case, use that wavelength 375 and V naught 1.87 volts, then find phi. Then in the second equation, we have lambda, we are supposed to find V naught in the second case, the lambda is 600, but phi can be taken from the value that we got in the first case. So let's see, for 375 nanometer photons, Hc by lambda or phi equals to Hc by lambda minus EV naught. So if you know phi, I can substitute this value of phi first 600 nanometer photons and find the V naught. That's simple as that. Now, as I mentioned in my previous class, it is easy to substitute this value. Hc by E is 12,400 into 10 power minus 10 volt meter. If you use this value, it is easy for our calculation. So what I do is, just like our previous questions, previous sums, I divide by E on either side. So it becomes phi by E equals to Hc by E into lambda minus, this becomes V naught. Now substitute this Hc by E, that can be given as, this value is 12,400 into 10 power minus 10 divided by, what is lambda? Lambda is 375 nanometers. 1 nanometer is 10 power minus 9. So what I can do is 375 into 10 power minus 9 meters. 1 nanometer is 10 power minus 9 meters. So since this is 10 power minus 10, I'll add one more 0 here. So it becomes 3750 into 10 power minus 10. So that I can easily cancel these terms. Minus V naught. What is V naught? It's 1.87. 1.87. Now this term will be in volts because this is in volts, this is also in volts. This is in voltmeter, this is in meter. Meter cancels up, then this term is volts, this term is volts. So dimensionally they are correct. So once we get this phi by E in volts, then phi becomes the value that we get into E, electron volts, we will get it. So what is this value now? This I can write it, I can cancel it, 0, 0, this 10 power minus 10, 10 power minus 10. Then 25 15ths. This is 25 15ths and this is approximately 25 phi's approximately. I'm doing some approximations. 50 by 15 is roughly around 3.3. Let's say it's 3.33 minus 1.87. So what it will be? 3.33 minus 1.87. 1.5 will be around 1.5 or 1.6. Let's take it more closer. 1.6 volts. Because we are doing some approximations, it will be roughly around 1.6 volts. We'll get. So phi by E is 1.6 volts. Therefore, phi will be 1.6 electron volts. 1.6 we will get. Let's check again. 3.33 minus 1.87. It should be 4. 1.46. 1.46 we actually get it, right? 1.46, not 1.56. Yes, 1.46 volts. So therefore phi is 1.46 volts, electron volts. So this is the work function. Now what I do is take this phi value and for the second wavelength we use this phi value here and we find out the stopping potential. So now I'll do it here itself. So for 600 nanometer photons, we have this equation. Phi is hc by lambda minus E V naught. Since we are supposed to find the V naught, let's take this on this side. E V naught equals to hc by lambda minus phi. You can take it like this. Hc by lambda minus phi is equals to E V naught. Now we have lambda, we have phi from here, we can find V naught. So E V naught is, what is hc by lambda? Again, I'll divide E everywhere, so it becomes V naught. V naught is hc by E, so that value will be 12,400 into 10 power minus 10 divided by lambda is 600 nanometers, so it is 6,000 into 10 power minus 10, right? Then minus, what is phi? Phi is 1.46 electron volts. So since I'm dividing it by E everywhere, I'll get 1.46 volts. 1.46 volts. I'm dividing it by E. This is electron volts. I'm dividing it by E. This will be phi by E. So phi by E will be 1.46 volts. Now simplify this. This will be 2 point, how much? 2.06, let's say. No, 20, yes, 2.06 around we'll get. minus 1.46. This will be roughly around 0.6 volts, right? Check the calculations again. So this is 2.06 minus 1.46 is 0.6 volts. So therefore, the stopping potential when wavelength is 375 nanometers is 1.87. Now the stopping potential when the wavelength is increased is 0.6 volts. The stopping potential, if you observe, it has decreased. Here the wavelength is increased. In the initial case it was 375, now it has increased. Means what? The frequency is decreased. When wavelength increases, frequency decreases. We know that C equals to nu lambda. From that relation, the frequency of this photon is lesser compared to the frequency of that. So when frequency decreases, the maximum kinetic energy value of the electron will also decrease, and when Ke max decreases, we know that stopping potential will also decrease. So yes, initial case it is 1.87, now it is 0.6 volts. So this is how we do it. We go to the next one. The surface of a metal of work function phi is illuminated by light whose electric field component varies with time as E equals to E naught times 1 plus cos omega t sin omega naught t. Find the maximum Ke kinetic energy. So this is omega naught t sin omega naught t. And find the maximum kinetic energy, maximum Ke of photoelectrons emitted from the surface. Let's read the question again. The surface of a metal of work function is given phi is illuminated by a light. Here the electric field is given, the varying electric field, the component of electric field component of light is given as E naught times 1 plus cos omega t sin omega t, omega naught t. Now we have to find the maximum kinetic energy of the ejected electrons. Now once you see this, let's go back to the electromagnetic waves. We know that the electric field E at any given time is E naught sin omega t or cos omega t. This is of that form. So let's split this. Let's expand the brackets first. We convert that into this form. Let's see what happens. Because for finding the maximum Ke, you should first find the frequency. If the frequency is known, then you can find the maximum Ke, because the maximum Ke depends on the frequency of light. Now see, let's expand this. E is E naught sin cos omega t. So what? I'll write E naught sin omega naught t plus E naught sin omega naught t cos omega t. right? So what I can do, this is sin A cos B form. I can still expand this. So E naught sin omega naught t plus, I can do this, E naught by 2 sin omega naught plus omega plus sin omega naught minus omega t. So sin of A plus B is sin A cos B plus cos A sin B, sin A cos B minus cos A sin B. So divide by 2, we will get this sin A cos B. So sin A is omega naught, B is omega. Now see, now in this electromagnetic wave, we have 3 different frequencies. One is omega naught, sin omega naught. Another is omega naught plus omega, omega naught minus omega. So this light is having 3 different frequencies. One is omega, then omega naught plus omega here, and omega naught minus, not omega, this is omega naught, omega naught, omega naught plus omega, and then omega naught minus omega. So 3 different frequencies are there. Now I told that the maximum Ke, the kinetic energy will be more when the frequency is more. You know, out of these 3 frequencies, which frequency is higher? Of course it is omega naught plus omega, because the other values will be lesser than this. So maximum kinetic energy of the ejected electrons will be because of this frequency. So now you write the equation. What is the equation? Ke max h nu minus phi. Ke max, maximum kinetic energy is h nu minus phi. What is nu? Omega naught plus omega. What is omega? We know that omega equals to 2 pi f. The angular frequency is given like this, 2 pi f. So nu will be omega by 2 pi, right? So f, instead of f I will use nu. So nu will be omega by 2 pi. So now which frequency I am mentioning? This frequency. So therefore Ke max will be h omega naught plus omega divided by 2 pi minus the work function is phi, it is given. So this will be the maximum kinetic energy for the photoelectrons ejected. Since 3 different frequencies are there, we have to choose the frequency which is maximum. Because of that maximum value for the frequency, you get the maximum kinetic energy for the photoelectrons. So the final kinetic maximum, Ke maximum, will be h times this frequency, omega naught plus omega by 2 pi minus phi. That's it. Moving on to next one. When light of wavelength lambda is incident on a metal surface, stopping potential is found to be x. Stopping potential is found to be x. When light of wavelength n lambda is incident on the same metal surface, The stopping potential is found to be x by n plus 1. Find the threshold wavelength of the metal. Threshold wavelength for the metal. Again, we are using two different wavelengths. One is lambda, one is n lambda. And when lambda is incident, the stopping potential is found to be x. We have to find the threshold wavelength for the metal. What is threshold wavelength? The threshold frequency is given by nu naught. It is the frequency required for the light when it is just sufficient to eject an electron from the metal surface. So threshold frequency is f naught, then threshold wavelength can be represented as lambda naught. So now we have to find this lambda naught. Two cases are given when lambda is x, when n lambda is x by n plus 1. So we'll do this sum in the next lecture.